Hello students, tomorrow is your IB physics exam, so let's solve this physics SL paper 1 from the specimen paper that IB has released. Right, without further ado, let's solve the first question. A car has an initial speed of 16 meters per second. It decelerates at 4 meters per second square until it stops. What is the distance traveled by the car? So we will use the equation v square equals u square plus 2as. The final velocity is 0. Why is that? Because it stops. And the acceleration is minus 4. Why minus? Because it's decelerating. So we get 0 square equals 16 square minus 2 times 4 times s. So we have 16 square divided by 8 equals s. This means that s equals 16 into 16 divided by 8, which is 32 meters. That's the answer for the first question. Let's move on to the second one. A block of mass 2 kilograms accelerates from a speed of 15 meters per second to 20 meters per second without changing its direction. What is the impulse acting on the block? We know that the equation for impulse is equal to the change in momentum. Now, what's the change in momentum? It would be the final momentum minus the initial momentum. Final momentum is mass times its velocity is 20. Initial is 2 times 15. This gives us a value of 2 times 20 is 40 minus 30. That's 10. 10 Newton second. Let's move to the third problem. A net force of 8 Newton accelerates a 4 kg body A net force of 8 Newton accelerates a 4 kg body from rest to a speed of 5 meters per second. What is the work done by the force? All right, so how do we do this? We know the force. The force on an object is 8 newtons, and the mass of the body is 4 kilograms, and the change in its speed is 5 meters per second. So one equation we can use is that the work done by the external force, all the energy in that work must have been converted to the kinetic energy. All right. So we can write work equals the change in kinetic, which is half times m times v square. This gives us 2 times 25. That's a value of 50. So A is the correct option. Let's move on. A person stands in an elevator lift. The total mass of the person and the elevator is 800 kilograms. So this entire system is 800 kilograms. The elevator accelerates upwards at 2 meters per second. So this entire system that we have here is accelerating up with 2 meters per second square. We are supposed to find the tension in the cable. So how do we do this? Let's use Newton's second law, which says that the total force on an object equals the mass of an object times its acceleration. Now, what are the forces that are acting here? We have the tension in the cable and the gravitational force. So I can write for the total force as Ft minus mg equals ma. I can rearrange this equation and write it as Ft equals ma plus mg. Now I just sub in the values for m, a, and g. So let's do that. So we get ma, mass is 800, acceleration is 2, and then I do m times g. That's about 9.8. So let's keep that as 10. This gives us a value of 1600 plus 8000. So that's a value of 9.6 kilonewton. So we'll choose option D. All right, let's move to the other part. Another question, which is an object is released from rest in a vacuum at height h. So we have an object that has been released at some height h. Let's say this is h, and it falls down. As it falls, it reaches some height of 0.75 h. We have to find the ratio of kinetic energy of the object to the gravitational potential energy. Now we know that energy is conserved. So the kinetic energy that it gains when it falls this distance must have come from potential energy. Now what's the drop in potential energy? The drop in potential energy would be mg times 0.25 h. That's the drop in potential energy. This has been converted to kinetic. So the numerator would be mg 0.25h divided by the gravitational potential energy at height h. So what's the potential energy over here? It's simply mgh. Mg goes away, h goes away, and we are left with 0.25, which is just 1/4. So the correct option is B. All right, let's move on to the next part of the paper. Okay, this is a very interesting question. So we have a beautiful bird that is resting on a thin rope. The rope is almost horizontal, as is shown here, and we are supposed to find the tension in the rope, give the correct relationship in the tension. Now we must realize that if an object, which in our case is the bird, it has to be at rest, then all the forces acting on it must be zero. Now, what are the forces acting on our bird? We have tension. It's pulling it to the right. Let's draw that neatly and go off like this. And the other part of tension, it's going to go off like this. Now, the sum of these two tensions, vectors, they must balance the weight. All right. So we'll use the triangle rule of addition. Grab this, place it over here, and now we see that the summation of these two vectors almost cancels weight. But have a look at the length that was required. It is much longer than the weight. All right, if it's much longer than the weight, we understand that the tension must be greater than the weight. All right, so this was a tricky one. So we would go with greater than W. Okay, let's press on to the to the seventh question. The internal energy of a real gas, mind you, this is a real gas, is zero. No, internal energy, if how can it be zero? Internal energy means the sum of kinetic and potential. If it were an ideal gas, the only energy in an ideal gas is kinetic. But we are talking about a real gas, so we need to take into consideration both the potential energy and the total kinetic energy. So it's option D, which is the correct one. Okay, moving on to black bodies. We have a radiation curve here, right? A body is at 600 Kelvin. Now what happens is we take another body at 450 Kelvin, and we are supposed to say how would that curve look like. Now if the temperature decreases, what happens to the peak wavelength? The peak wavelength is going to shift to the right. Not only that, the peak itself is going to fall. All right, we are going to have a smaller peak, and we are going to have a peak that shifts to the right. All right, so we have some happy viewer here. Thank you for your support. So what happens to the peak is it's going to go down and shift to the right. Okay, so that's over here. Peak shifts down, it goes to the right. So we'll go with option A. Okay, let's move on to the next part of the problem, to the next question. Star X has luminosity L and apparent brightness B. And we also have star X, the star X is at a distance D. So let's make a quick sketch. We have star X, okay, and if this is our, maybe let's draw it like this. This is our star X, and its apparent, and this is Earth, and it's at a distance D, and its brightness is B. Then we have another star Y that has the same apparent brightness, but it's 4 times more luminous. Let's suppose the star Y is at some distance D dash. Okay, now it has 4 times, its apparent brightness is 4 times, is the same as X. So its apparent brightness is the same, but its luminosity is 4 times. If this is L, the luminosity of star Y, the luminosity of star, if the luminosity of star X is L, the luminosity of star Y is 4L. Okay, so we can write a relationship that is luminosity, or rather brightness, equals, we'll use this equation, equals luminosity divided by, brightness equals luminosity divided by 4 pi d square. Let's apply this relationship onto star X. So we get brightness of star X is its luminosity divided by 4 pi d square. And the other equation is brightness of Y is luminosity of star Y divided by 4 pi d dash square. Now what is given is that it has the same apparent brightness, meaning brightness of X is the same as brightness of Y. So let's equate them. So we get Lx over 4 pi d square equals Ly over 4 pi d dash square. Okay, 4 pi and 4 pi goes away. We also know that star Y is 4 times more luminous. So luminosity of Y is 4 times the luminosity of X. So I'll write 4 times luminosity of X. So Lx goes away, and we are left with 1 over d square equals 4 luminosity 4 over d dash square. Okay, we are trying to solve for d dash. We'll get d dash square equals 4 d square. If I take a square root both sides, I get d dash equals 2d. And that means it's option B. Okay, let's move on to the 10th question on circuits, which is 4 identical resistors, each of resistance R, are connected as shown. What's the effective resistance between P and Q? If we look at this set of resistors, they're all connected in series. So I can put them together and call this 3R. Then we have this resistor PQ that is in parallel with the initial one. Okay, now we can use the equation 1 over the total resistance is 1 over R1 plus 1 over R2. If we solve this, we get the total resistance to be 3R over 4. So that's the total resistance, 3R over 4. All right, let's move to the 11th question. Conductor X is connected to a cell of EMF E, and it dissipates 16 watts of power. Conductor Y is made from the same material, but it has twice the diameter. Sorry, has the same diameter, but is twice as long. It's connected to a cell of EMF 2E. What is the power dissipated in Y? So I'm going to use the equation power dissipated equals the voltage V squared over R. If I apply the equation onto X, I get Px equals Vx, that's the EMF squared over R. If I apply the equation on Y, I get Py equals the EMF squared, which is 2E squared divided by the resistance. Now, what's the resistance of Y? We know resistance equals resistivity length over area. And what has happened to the area? It has the same conductor Y is the same diameter. So it has the same cross-sectional area. But what happened to the length? It is twice as long. That means the resistance in Y is twice the resistance of X. So I'm going to write 2R over here. Now I can solve this, make this simpler. This will become 4E squared over 2R. This becomes 2 times E squared over R. What's E squared over R? It's the power dissipated in X, which is given to us, that's 16 watts. So how do 2 times 16? This becomes 32 watts. So that solves this part. Let's move to the 12th question. Container X and Y are filled with an ideal gas at the same pressure. And the volume of, so if this is our container X and this is container Y, they are at the same pressure. Let's call that P. Volume of X is 4 times. So if this is V, this will be 4V. The temperature of X is 327 degrees Celsius and the temperature of Y is 27 degrees Celsius. So we are supposed to find the amount of substance in X divided by amount of substance in Y. In other words, we want to find Nx over Ny. Let's apply the ideal gas equation. We have Px, Vx equals Nx or Tx. Apply the same equation onto gas Y. We have Py, Vy equals Ny or Ty. We can divide these two. R and R goes away. They are the same pressure. The pressure thing cancels. And we are left with, if I do that, this goes away, R goes away. We have Vx over Vy. Now what's Vx? Vx is 4 times Vy. So I'll do that. This is 4 times Vy. Then Vy is going to cancel. And I'm left with 4 equals Nx Tx over Ny Ty. All right. Let's solve for Nx over Ny. If I do that, Nx over Ny is 4 times the temperature of Y over the temperature of X. Okay, what's the temperature of X? Keep in mind that we should always use the Kelvin temperature. So we need to add 273 to every temperature that's in degrees Celsius. Now what's Ty then? It would be 27 plus 273, that will be 300. And what's the temperature of X? The temperature of X is going to be 327 plus 273, that will be 600. This goes away with this. We get 2. 2 goes away with 2. So we get a value of 2. Right? So that solves this question. Let's move on. Question 13. An electromagnetic wave has a wavelength that's about the size of the diameter of an atom. Now, what region of the electromagnetic spectrum does the wave belong to? Well, you can just look up the electromagnetic spectrum, look up the size of an atom. This question kind of needs to be memorized. And the answer, I'm just going to give you the answer. It's X-rays. X-rays have the same wavelength as that of an atom. Question 14, a particle undergoes simple harmonic motion of period t At t equals 0, the particle is at the equilibrium position. At what time is the particle at the greatest distance from its equilibrium position? So if I real quick draw an axis, this is the equilibrium and this is our particle. Now how much time does it take for one complete trip? For one complete trip, it takes a time of capital T. That means it takes time T over 4 to go to the right, to come back it's T over 4, to go to the left it's T over 4, another T over 4 when it arrives. So when it's at the extreme, the time is either T over 4 or it's 3T over 4. And that option is given to us, so we'll go with that. 3T over 4. Okay, let's try the question. Let's try question 15. Diagram 1 shows the variation with position of the displacement of a standing wave formed on a string. Diagram 2 shows the variation. Thank you for your support. So diagram 2 shows the variation with position of the displacement of a traveling wave moving to the right along a string. Points P, Q, R, S are points on a string. What's the phase difference between P and Q? Well, on a standing wave, we must keep in mind that in a standing wave, the wave either totally goes up, goes flat, and then goes down. So all the points, they are in phase. The wave either goes up, the standing wave, then it flattens, then it goes down, and it keeps on oscillating like that. So points P and Q vibrate in phase. So the phase difference between P and Q is 0. But what about R and S? This is a traveling wave. What's a traveling wave? A traveling wave is a wave that moves. It's not like a standing wave. So if we have a crest and a valley, what happens is that the wave will move forward. That's the traveling wave. All right. Now what's the phase difference? If you look closely here, the path difference is a quarter of a wavelength. All right, this is a quarter of a wavelength. We know that one wavelength corresponds to a phase difference of 2 pi. If I divide by 4, I get a phase difference of pi over 2. Okay, so that's the phase difference between R and S. It's pi over 2, and the phase difference between P and Q is 0. So we'll go with option C. Let's move on to the 16th part of the question, part of the paper. A mass of 0.25 kilograms hangs from a spring. What's the natural frequency? You know the equation for time period is 2 pi square root mass over m over k. And what would be the frequency? Frequency is simply 1 over the time period. That would be 1 over 2 pi, and we need to invert the root, k over m. So you would take k as 4, m as 0.25, and push it here, and out will pop the value for frequency. I'll skip it, and I'm sure you'll be able to solve it on a calculator. All right, let's try the 17th question. We have two wires, P and Q. We have the same current flowing through them, and the distance is d. Now what happens is that the distance increases to 2d, um, and the current decreases by 1/2. What happens to the magnetic force? On your data booklet, you will see an equation for F, that is mu 0 I1 I2 divided by 2 pi, r is the distance. Now if one of the current falls by half, and the distance, what happens to the distance? It also increases 2 times. What would happen to the equation? The new equation would be a mu 0 I1. We have I1 divided by 2 pi 2d. Okay, this becomes 1/4 of the initial force. So that's F over 4. Okay, let's move on to the 18th question. Planets X and Y orbit the same star. The distance between the star X is 5 times greater than the average distance between planet Y and the star. What's the so we have to find the orbital period of planet X over orbital period of planet Y. I'm going to use Kepler's law, which says time period is proportional to R cube. So I would write this equation for X, time period of X square is proportional to Rx cube. Write the same equation for Y, time period square is proportional to Ry cube. Let's divide these two equations. What would we get? Tx square over Ty square equals Rx over Ry cubed. Okay. Now what's Rx? The average distance between planet X and the star is 5 times. So Rx is 5 times Ry. So I'll plug in R5 times Ry. This and this goes away. So we are left with Tx over Ty square equals 5 cube. Okay. That means Tx over Ty is going to be a cube root of cube root sorry, square root of 5 cube. So the correct option is D. Let's move on to the 19th part of the problem. A charged rod is brought near a neutral metal sphere. So we bring a charged rod near this neutral sphere. When the sphere is grounded, we mean that this end literally is touching the ground, and charges can flow up or down the wire. Now, what happens is that there's an electric current for a short time between the ground. The ground is then removed. We remove this connection, and we are supposed to find what kind of charges exist on the rod and the sphere. So what happens here is the ground, it's full of electrons. Okay, it's a sea of electrons. And once you bring this charged rod near the sphere, these electrons begin to flow and charge the metal sphere. Okay, there's an electric current from the sphere to the ground. So it's said that the current flows this way, meaning that electrons are flowing the opposite way. So what kind of charge should have been here to attract electrons? These must have been positive. So the correct option is a positive charge on the rod and negative charge on the sphere. So that solves this. Let's carry on. A positive charge of magnitude 1 microcoulomb is placed here, and a point charge q are separated by a distance d. So we have some point charge over here. If I place an electron here, then the force on the electron is 0. Okay, the force on the electron is 0. We know this is a positive charge, so there must be a force of attraction between electron and this 1 microcoulomb. Then, in order for this electron to be at rest, there must be a force of repulsion. Where does that come from? It comes from this charge. That means this charge must be negative. Okay, since you have increased distance 1, so what's the distance between the electron and the charge? It's 2d. Okay, we know the force between charges is given by this equation, q1 q2 over d square. Okay, now if I increase the distance twofold, the charge must increase fourfold in order to balance the force due to this. So the answer must be minus 4 microcoulomb. All right, let's move on to question 21. What's the sequence for the evolution of a main sequence star that's about 2 solar masses? If it's 2 solar masses, it's not a really massive star. That means it's much like the sun. Its evolution will follow the same path as our sun. And what's that? It will become a red giant. Then it's going to shed its outer layers and become a planetary nebula and then turn into a white dwarf. So we'd go with option B. Okay. Right, now we have question 22. The diagram shows the emission spectrum of an atom. So what happens here is we have increasing wavelength to the right. That means these Uh, s- these lines to the right represent lower energy. So this is less energy to the right, less E, and this is energy, more energy. Okay. Now, when an electron jumps between two levels, it's going to emit radiation. Okay. So when an electron, say, jumps between these two levels, the energy gap is very small. That means it's going to emit a large wavelength. A large wavelength corresponds to a small energy, that's this. All right. So right now we have a tie between A and C. But next we see that these wavelengths are bunched together, corresponding to the same energy gap. Between C and D, sorry, between A and C, we see a different energy shift. If I drop this, if a photon, an electron drops between these two energy levels, it's going to have a larger, it's going to emit a photon with a larger energy, means a smaller wavelength. That's represented here. A smaller wavelength, a larger energy. What if an electron jumps between this level and this level? That's an even larger jump, meaning an even larger energy, hence a smaller wavelength. That is shown here. So we see that option A matches the most with this spectra, so we'll go with A. Okay, on to question 23. We have two radioactive samples and they have the same half-life. Initially, the ratio of activity of X to activity of Y is 4, and we are supposed to find the ratio after two half-lives. Okay, so now the activity of X and activity of Y are going to fall by the same rate. In one half-life, the activity of X is going to fall half its original value. In another half-life, it's going to fall another half-life, another factor of half. So the activity is 1/4. The same is going to happen to Y. It's going to fall half its original value, then again half its original value. Now we want to divide this activity with this. It's the same thing as we had earlier. Half and half will cancel. We have the activity of X to activity of Y, which is 4. So the correct option is D. Okay, let's try the 24th part. Three statements about a nuclear fission reactor are. Well, in a nuclear fission reactor, you must remember there are two important components. One is the control rods. What do they do? Well, if you, these control rods are literally like rods, you immerse them into the reactor and they absorb neutrons. So if they absorb neutrons, the rate of reaction decreases. Okay, we don't want it to go out of control and create a bomb. We don't want to do that. We want to control the rate of reaction. So we place a moderator there. Sorry, a control rods in there. So control rods must be good absorbers of neutrons to control the rate of reaction. And what does this moderator thing do? Moderator inside, so when a neutron is emitted, it moves very fast. If it moves so fast that it's not able to react with the uranium nucleus and cause more fission. So what do we want to do? We want to slow this neutron down so that so the uranium is able to absorb it, and hence we have a sustained chain reaction. So the moderator must slow neutrons. So option 2 and option 3 are correct. The heat exchange transfers from fuel rods to the moderator. That's not true. Fuel rods are there, as they say, just for fuel. So we'll go with option 2 and 3. So that's C. All right, I think this is the last question. The HR diagram shows two stars. We have two stars, X and Y. We are supposed to find the radius of X over the radius of Y. How do we do this? Well, they have the same luminosity. That's the first hint. And the temperatures are given. So what do? We use the equation luminosity equals sigma A T to the 4. For X, it's going to be luminosity of X sigma A, temperature of x to t to the 4, and then luminosity of y would be sigma, its area, this is area of x, area y, dy to the 4. Let's divide these two equations. Sigma goes away, and we get luminosity of x over luminosity of y, but they're the same, right? So that's 1. Yeah, 1. So we get 1 uh, equals ax dx over 4, ay dy over 4. Okay, let me rearrange this. We get ax dx over 4 equals ay dy over 4. Now what's ax? Ax is the surface area of the sphere of the star. So we get 4 pi radius x square dx4 equals 4 pi radius y square dy to the 4. 4 pi goes away, so let's get rid of that. What do we want? We want Rx over Ry. So let's write that. We get Rx over Ry equals dy to the 4 over tx to the 4. Okay. So if I take square root both sides, what do I get? Rx over Ry equals dy over tx square. Now what's dy? Temperature of y is 10,000 and temperature of x is 40,000. So if I do that, 10,000 over 40,000, what would that be? That would be 10,000 over 40,000. And we square that. This goes with this, goes with this. So we have 1 over 4, and you need to square that. And that's 1 over 16. And that's option A. I hope you found this video helpful. If you want some more videos, comment in the comment box wherever it is, and I'll come up with a paper to stream. All right. All the best with your exam. And my final tip would be don't get stuck with any particular problem. If you're stuck with some question, leave it there. Try another one. All the best. I'll see you then.